Hi, welcome to another session on pointers in C. We'll start the session with a quick recap of what we did in the last session. That's the dynamic memory allocation. We'll do a quick recap and probably have some new examples, and then we will see today another topic in programming in C, which is called compiler directives. So yesterday we looked at how does memory gets allocated when a process or when a program starts running. We saw that there is some part which is called as permanent storage, and we saw how stack is controlled by the program execution. We saw how stack frames get created dynamically when the functions are called, and how dynamically it's taken away when the function returns. We also discussed the necessity of a space in main memory for programmers to play around with the bigger data that they want dynamically. We call that space in memory as heap, and we also saw how memory can be allocated and deallocated on the heap, and we also did mention that the allocation and deallocation of the memory or of the space in heap is totally controlled by the programmer, and we also saw 4 functions which actually help the programmer to perform these functions. So we saw specifically malloc, calloc, realloc and free, but we discussed malloc and free extensively because those are the generic ones. So in fact, free is the only method that we use to free the space in heap, whereas malloc is the generic function that we use to create space on heap. Calloc and realloc is basically extensions or extensions to malloc. So if I have a program like this, what happens for this instance of the program is on the stack of a stack frame is created for main, and you have A, N and PA allocated on the stack. So the pointer is allocated on the stack. But when we actually do this scanf function, which is dynamically, you are at runtime, you are trying to get the value for N. So what happens is that the modifications that you do here, you send the pointer to the method scan, and the pointer actually the method actually updates the contents of this stack. So you were already exposed to this earlier. So what we looked at yesterday was how to allocate some space on heap. So this is what we did. We used malloc. So malloc returns a void pointer. So I typecasted it for integer, and then I gave the size basically n, which is the runtime size that I got from the previous statement, multiplied by the size of integer. So that is the amount of bytes that I am asking the machine or asking the operating system to provide. So what operating system does is it gives a random space, contiguous block of say 400 bytes, assuming that each integer requires 4 bytes. So we got a space of 400 bytes, and then we can use the pointer arithmetic or the dereferencing of the pointer to assign values on the heap. So we did that by using star PA is equal to 100, the number went there, PA plus 1, the number went here, and still the remaining bytes were free. We also saw another mechanism to initialize that. We set up a for loop, and within the for loop I used pointer arithmetic along with the dereferencing operator star to assign some values onto the heap. So you have 0 to 99. Now all the 100 integers have been assigned now. So instead of this assignment, you can also use a scanf statement where you read interactively from the user and populate the array or the space in the heap appropriately. What we did not mention yesterday is it is the job of the programmer, after performing the job after performing the use of the allocated space on the heap, it is his responsibility to free it. So that occurs only when you have to use the same pointer again for some other purpose. So before you actually do this, before you use PA, which has been now assigned to point to some space in heap, it is necessary for you to free it. Okay. So yesterday we did mention some of the common mistakes that the programmers do. using a pointer before allocating heap space. So, integer star pointer and integer star pointer is equal to 5. So, basically what we are accessing is basically the stack. Okay, we are not allocating the heap space. Okay, so changing the pointer and not the value it references. Many people do this. Pointer is equal to 10. So, this is what the modification that you do here happens to the stack. In fact, in this case it could end up into a runtime error. Okay. So, forgetting to free space on the heap. So, that is what we discussed in the previous example. So, you have 2 pointers and you have allocated some space to it, and if you want to do P1 is equal to P2, you are overwriting the pointer value P1. So, now it is your job to see that the allocated space, which is this, is freed. So, that is one more common mistake that most programmers do. So, we will now re-emphasize that with a couple of examples. So, suppose see this program illustrates something. You create a pointer, you allocate some space on the heap, you use it, you free it, and then go along. So, this is a program where I am allocating I am defining a pointer and allocating some space. So, this is basically max line, which is 80 characters here. So, I am allocating some space of that 80 character space. Okay. So, that is what you allocate. So, when you do this statement, what happens is on to str is str is allocated on the stack, and a call to heap is done. So, you get this 80 bytes because the length of character is 1 byte. You get 80 bytes, an array of 80 bytes, and then you create this space. So, these values will not be there. You have just created this space, and the value on the address of the first byte of this block is 23, which is assigned to str. So, that is what happens. So, 23, which is the content of str, is on the stack, and 23 is basically referring to an address which is the starting address of the block of 80 bytes that you got. Okay. So, now you use scanf function, pass the pointer str to it. So, you know, everybody knows what happens. So, when you do this, it accepts a string from the user, inserts a /0 inherently. You need not key in this /0. So, it inherently inserts this and returns this. So, this is what you get when you do scanf %s. This is what you get. So, now you can use the values of that, and before you actually go ahead and use this str for something else, it is your responsibility to free it. So, yesterday we also noted that when once you get allocation on the heap, it is persistent. It goes on until you execute a free with respect to the pointer that is pointing to the starting of that block, or the program terminates. This is the correct usage of the pointers or the space in heap. One more example, in one line declare the pointer variable. This is just to re-emphasize how you have to use the space on the heap. So, it's when you declare a pointer variable, you are basically placing it on the stack. So, allocate memory on the heap. So, you do that basically using malloc or calloc, and set the value of the pointer variable equal to the starting of the heap. So, both malloc and calloc does this for you. Read a value from the user into the space on the heap. This is why scanf takes the pointers as the parameters passed in. There are other mechanisms to read the values into the heap. Okay, you will go. You can read it from a file. You can read it from. You can pipe the input from another program into this program. There are multiple ways, and those you will learn a little later. So, once you are done with the usage of the space in memory, it is your responsibility to release it. So, release all the space on the stack pointed to by the str, and set the value of str pointer on the stack equal to the null or to a new value. So, as a last example, we will see how we can create two-dimensional arrays using pointers. So, to really make things confusing, you can have pointer to pointers. They are very useful as well. It is not just we are not specifying this example just to confuse you. There is a significant usage of this because you need two-dimensional matrices significantly when you operate on matrices. So, this comes in handy whenever a two-dimensional array is required. You can also declare 2D arrays but generally it goes on. I mean, if you declare it within a function, it is statically allocated number 1, and generally it goes onto the stack. Okay. So if dynamic memory is needed, that means you want a 2-dimensional array, but you don't know the size of it during compile time. When you write the program, you don't know what would be the size of the matrix, and when the size of matrices are big, it is unnecessary or it is inefficient for us to create large amount of space on the stack, because in the last class we saw that stack is limited in size for every program running on a particular operating system, and if you the sooner you fill the stack, you will run out of the space and you cannot run your application on the machine. So declaring a pointer to a pointer is fairly simple. We have seen couple of things before this as well. Just put 2 asterisks in front of the variable name and you get it. So one example is character ** names. We will quickly see probably 2 examples. So one for some advanced C programming, the other just to understand the concept of 2D pointers. So what I have is integer ** 2D. So that's the variable that I declare. Okay, so what is this? This is a pointer to a pointer data type of integer. So integer *2D is pointer to integer, and this second star here specifically mentions the pointer to the pointer of integer data type. So now how do I allocate? When I use double pointers, how do I allocate? So I use 2D is equal to integer **. Integer ** is pointer to integer pointer, malloc 4 into size of int. So this could be anything. So I just want 4 spaces for integer, or 4 spaces in the heap for the integer. This is exactly what happens. If I execute this statement, you have this, each one of them can hold an integer pointer. Please note, so each one of these can hold integer pointer. That's why I have said integer * here, size of integer *. Okay, and I have also typecasted as pointer to pointers. Okay, I get this space. Okay, so now what do I do? So I can go on allocating say blocks of storage to each one of these pointers, but remember that this is also in heap. So in all previous examples, so we had this in the pointers used to be on stack, and then it was referring to heap. So now I have already used one pointer to point to a pointer of pointers, okay, into this 4 spaces. Okay, so in fact this should end at 3. Okay, so just pardon me for that. So this should be 0, 1, 2, 3. So you have 4 spaces. So I can go on allocating space to that. I have shown one of them, *2D plus 1, that is content of 2D plus 1, that is this space, the space here. I have allocated a block of 40 bytes, 40 integers on the heap. So this is the block of 40 integers, and the starting address of that is 400, and that gets written here. So similarly, I can use the other locations. So this is an example where I can use 2-dimensional. I can implement 2-dimensional arrays. So I have this in the heap. So as a final example, we will see what we call as the arg vector or argument vector in C. Okay, so I don't know whether you have seen this before, but definitely it makes sense for us to see here. Up until now, the main has been written as int main without any arguments and begin and end. So there was nothing that was written between these 2 parentheses. This is okay, but it's usually written as int main integer argc character ** argv. Okay, so what is this argc and argv? This argc is basically number of command line arguments being passed in. This counts the name of the program. So we will see this, what exactly this means. So generally you say you would have executed your program as a.out if you are using a Linux or Unix environment. If you have used a Windows environment, you would have executed as a.exe. So that happens to be the first argument of the command line. Those of you who are familiar with Unix might have used something like cat, file name, and maybe pipe, and then say more. So cat is the first say argument of the command line, then file name is the second argument, pipe is the third argument, more is the fourth argument. So how many arguments you have? The cat, the file name, the pipe character, and the more. So you have 4 arguments. Okay, you have 4 arguments in this. So this argc basically captures that. And what does argv stores? So argv basically correspondingly stores the substrings of the command line. So the first will be the command, which is in this case the example that we are taking is cat. argv0 will contain that, argv1 will contain the file name, argv2 will contain the pipe symbol, and more is present in argv3. So we will again see that with another example. Okay, basically this is an array of strings, a 2D character array. Each string represents one command line argument. So we will see that specifically. So we see this integer main argc argv. So we have used the main, or we have started the main with this variety, then integer I, and then printf number of arguments %g/n argc. Okay, you can do that in your labs. So for I is equal to 0, I less than argc, I plus plus, I can print the each element in the argument vector. So given the following example, so this is the prompt that you get. So it could be Unix prompt or the Windows prompt. If this is the command that you give, example -o option required. So what happens? The number of argument is 1, 2, 3, and 4. So any string that is present between 2 blanks is taken as one argument. So you have example number 1 -o option required. You have 4 arguments. So your argc will be 4. The argc will be 4. Argument 0 will be example. Argument 1 will be -4, and so on. So argv0 will be this, argv1 will be this, and so on. So what happens actually in the memory? So when you create, or when the function main is called, you have argc created here, argv created here, stack is created here. So onto the stack you have I. So that's what you have declared here, integer I, and 0 gets assigned to that. argv and argc. So argc gets 4, argv gets 220, which is the base address or the starting address of this block of memory locations. So how many elements are there? Exactly equivalent to the argc. So a block of 4 pointers, character pointers, is present here. So 220 happens to be there. So this 220 actually gets onto the stack, but this is in heap. So argv0 now stores example, argv1 stores -o, and argv2 stores option, argv3 required. Okay, if you understand this example, so you are more or less actually understood all the say characteristics of 2D pointers. So you have this example. We have done the same thing. You have character star names pointed to pointer of characters. Then you have malloc, the 4 size of characters. So and then in this you have this character basically an array of characters of 80 size, and you have 4 such, and now you assign the names to that. So this is basically how we could implement argc and argv in the example. So once you really understand the example that we discussed previously, that is this. Okay, so in this basically if you correspond to this is what we are creating in the first malloc statement. In the second malloc statement, actually we are creating these 4. So in the for loop you have this 0, 1, 2 and 3. So you are creating this. Okay, let's take a closer look with one more example. Okay, so sorry, so this is exactly what happens with respect to this program. So you get 220 here, the address of the starting block of this 4 pointers, and then you reserve some space for each one of them. So this is a character, sorry, an array of characters of 80. So, similarly, all of them are like that. This is what actually happens in the for loop with a malloc, okay, and this is what we set up. So, we will discuss calloc to a little extent because it is an extension of malloc. We will not discuss realloc because it requires fair amount of understanding of what happens to malloc and callocs, and very rarely we are going to use that. So, we will not discuss that much. So, what happens in calloc is exactly equivalent to malloc, but along with allocating space in the heap, it will also assign a 0 value to the allocated space. So, for example, I have integer star array is equal to integer star malloc 10 into size of int. You are all familiar with this. This will return a block of 10 integers, space, a block of space which can hold 10 integers. This block is contiguous. Okay. So, what does this do? Integer star array, integer star calloc 10 comma size of int. So, this also allocates the same space, except that in this case the allocated space are also initialized to 0. Okay. So, you can use calloc and malloc wherever it is appropriate. So, people are very conversant or very convenient or very comfortable with malloc. So, you can also use callocs. This is what we have done. Okay. So, we were supposed to discuss all the issues in pointers. We discussed almost every topic in this. So, one of the toughest say concept in C is dynamic memory allocation. We have spent sufficient time in understanding that. So, we started with pointers and then we started with pointer and function arguments, how it will empower us to write functions which can return multiple values. Then we saw how pointers and arrays are closely related. We also saw how address arithmetic is different from integer arithmetic, because we know that addresses are basically unsigned integers, but the arithmetic is not exactly similar to integers because there is a size factor that comes into play. So, then you saw character pointers and functions. Specifically, we saw how character strings or variable length character strings can be handled with a beautiful example of argument vector in C. We saw dynamic allocation, how to initialize pointer arrays and so on. Okay. So, that closes or that concludes the discussion of pointers in C, but the topic is so complex and hence so vast. So, until you get fairly comfortable with pointers and then how you allocate and deallocate space or manage space in a heap, you are still not a complete C programmer. Okay. So, understanding how you can efficiently use C decides how good a programmer are you in C. So, we will move on to the next topic, which is basically the C processors, C preprocessors. Okay. So, we are supposed to see all these 4 subtopics of this. So, we will start with understanding what a preprocessor is. We will see macros, very simple concept. We will see compiler control directives, very strong concept, but at this point of time, because most of you are beginners in programming and you are not writing or you have no experience of writing large C programs, you may not be able to appreciate this compiler control directives, but it is good to know that there is something called as compiler control directives, and when you start beginning to write large programs, you need to revisit this concept and see how you can write better when you are handling big programs. We will take some small programming examples as well. So, the preprocessor is a program that processes the source code before it passes through the compiler. So, in the beginning of this course, you must have seen that once you write a source program using C programming language, you use a compiler to compile it. So, compiler basically checks for the syntax. If there is any syntax, it throws out appropriate error messages. And once the program is completely syntax free, or sorry, syntax there are no syntax errors. Okay. So, then you will get an executable code which you can run it on the machine. But there is another say processing that gets done before the compilation, which we call as preprocessor. So spare me for the spelling mistake of the preprocessor. Okay, so the preprocessor, the spelling is this is right, so there's some typo error here. So preprocessor is basically a program which takes the C program that you have written as an input and generates another C program. So what it does we will see today. Okay, and the output of preprocessor actually gets into the compiler. So the compiler that you use will invariably use preprocessor, but there are systems or there are environments where you can invoke only the preprocessor. Okay, you can invoke only the preprocessor, but if you generally invoke the compiler, the preprocessor is automatically invoked. So the program has to first pass through preprocessor, the preprocessor has to do its job, and then the compiler takes the output of the preprocessor and does the job, and then goes to the linker, and then you get the binary code. So we will restrict our discussion only to the preprocessor. So preprocessor is a program that processes the source code before it passes to the compiler. It operates under the control of directives. We are going to see some of the directives or most of the directives. So basically directives are placed before the main lines. When you have a C source program, so you must have all remembered there is something called as hash stdio.h. That is what we are going to discuss today. What is that? So is there anything else that stdio.h people must have told it is a header file, it is somewhere in the library, but we will see how to write something of that kind on our own. Okay, and what should be written in that. We will see that today. So to begin with, we will see some of the directives. So directive means basically an instruction to the preprocessor. Please remember that this will not generate any machine code. So directive is just an indication to the preprocessor to do something. What needs to be done depends on what is the directive that we use. Please remember that directives are only indication or directions to the preprocessor. There is no machine code that gets generated here. The machine code is generated only by the compiler. Okay, hash defines a macro substitution, that is the simplest concept which most of us use very liberally, and then you have something called as hash undef, hash include, hash ifdef, endef, hash if endef, hash if else. So because we are going to discuss each one of them, let me not just bother you about reading this. So some of this is very familiar to this. So you know the if statement, there is an end if here. You know there is an if statement, there is something called as if def. You have seen include, you have seen def, but you are seeing undef. Then you if and else you have already seen in your code, but all this is now tagged with an hash prefix. So whenever preprocessor sees a hash, it knows that this is the line that I need to process. The rest of the line it simply skips. So the preprocessor. So let's see now quickly. Macro substitution. So this is the simplest concept. Those of you who have studied assemblers, I doubt anybody would have done at this point of time, will know what this is. So macro substitution is a process where an identifier, everybody knows what an identifier is, it's just a name, in a program is replaced by predefined string composed of one or more tokens. So something like this, hash define, I give a name, let me call it as identifier, and I give a string to it. Everybody knows what a string is. It's a sequence of characters. Okay, so hash define some name, identifier, and then string. So the string may be any text. The identifier must be a valid C variable name. All the rules that are applicable to variable names in C applies to this identifier as well. Okay. So forms of macro substitution, simple macro, argumented macro, nested macro, all of this we will see. Let us see some simple macro replacement. So we use it for simple string replacement. So basically when you want to define some constants, say for example you are writing a very large program and there are some constants in that large program. So many a times what would happen in projects is when you have to implement an application, you write your source programs across multiple files. So typically projects are done in groups. each programmer in the group is allocated some logic to be implemented. Okay, he will create the source files in his own way and keep it. So, I will not bother you much about how the project is done, how the projects get distributed and all, but please remember that when you write large applications, it is impossible for only one programmer to write, especially when the time is when time is the constraint. So, what do? We divide the problem into smaller problems and assign some sub problems to an individual programmer. So, there could be 10 programmers working on the project, there could be 20 programmers working in the project, and each programmer will be the custodian of multiple source files. But now, when you have for across all these programmers, assume that you have some set of constants, which is the same across all the programmers. So, what do? We define all those constants like this and keep it in a file. Okay. So, I define count as 100, false as 0, subjects as 6, pi as this, capital of something as Seoul. Okay. So, this is the variable name that we talked about. This is the string that that we talked about when we started discussing macros. So, a definition such as hash define m5, what does it do? So, this is read by the preprocessor. Now, preprocessor knows that every time I see an m in the rest of the code, I should replace it with 5. Okay. So, this is an indication or the direction to the preprocessor that every time I see a capital M in the program, I should replace it with 5. This is a simple example. So, for example, now in the program I have total is equal to m into value, I have print m is equal to %d/n comma m. So, for the preprocessor, whether it is a literal string or something, it does not matter. For the rest of the code, every time it sees a capital M, it will replace it with the string. But please remember that it should have a blank on either sides, only then it recognizes it as a token. Okay. So, what will be the output of the preprocessor? If it finds a statement like hash define m5, in the rest of the program, in the rest of the lines of program, wherever it sees m, okay, please remember m with 2 blanks on either sides. So, it will replace it with 5. I get 5 into value. Okay. So, if it is there in the literal, it will not go and change, because literal, you remember, it is a constant. Okay. This is a literal constant, and then you have 5. Is that clear? Okay. Let us see some more example. A macro definition can include more than a simple constant value. I mean, just see this. Define area 5 multiplied by 12 into 4 6. Define size of int multiplied by 4. So, this entire string from 5 to 6, 5 start 12.46, this entire thing is the string. Now, wherever it finds area, wherever the preprocessor finds area, it will replace with this string. Similarly for the others. So, consider now the evolution of ratio a by d. So, this is there in the program. So, the compiler directives before actually the preprocessor reads this, it would have read the definition of d and a. D is 45 minus 22, a is 78 plus 32. Now, this ratio now after the macro substitution becomes what? 45 minus 22 divided by 78 plus 32. So, what is 45 minus 22? It is defined as d, it is defined as 45 minus 22. Now, whether you want this, or you wanted 45 minus 22 whole thing and then divided by 78 plus 32, it depends on what you want. So, if you want to avoid any ambiguity, if you retain this as it is, 22 by 78 gets evaluated first, and if that is not what you wanted, you need to do, or you need to use parenthesis. So, make use of parenthesis if you do not want any ambiguity. The preprocessor performs a literal text substitutions. So, what does preprocessor do is it reads files one by one, line by line. Whenever it finds hash define, we are discussing only macros. Whenever it finds hash define, it sees whether it is syntactically right. So, hash define. So, there should be an identifier followed by a string. So, what it does for the subsequent lines, once it sees a definition, the subsequent lines, wherever it finds that identifier, it goes on replacing with the string. Okay, now let us see. So, I have this small piece of code, start integer total is equal to 10, average is equal to 20, count is equal to 0. Does this look like a C program? Definitely not. So, I think none of us have seen a C program like this. Okay. But if I pass this to the C compiler, it will throw out errors. But what happens before you actually call the C compiler, the C preprocessor kicks in. The C preprocessor does its job, and now we will see what happens. Suppose if this is the definitions that is defined in the program. Hash define equals is equals, hash define and is ampersand, hash define or is equal to pipe, define hash define not equal to this, and so on. Assume that this is the definition that the preprocessor sees, and then it sees this block of code. Okay, what it does? It looks at start. Is start defined? Start is a token. Is start defined? Yes, it is defined. What is it defined? Int main open parenthesis, close parenthesis, and the braces. It replaces this start with this, and then it goes on doing that and ends up generating this. So, this is what the preprocessor saw, and this is what it outputted. Okay, in the output you have this int total is equal to 10, average is equal to 20, perfectly valid C program. Okay, remember this example, you have understood what macros mean. Okay. So, there are some rules for macros. When you start developing large programs, you will study that, you will understand it much better, but all computer science students, all programmers should know what is macro substitution irrespective of the language. You may start coding in Java, coding in C++, all programming languages will provide you what we call as macro substitution. Okay, it comes in very, very handy, as I said, when a project which is very large is involved and multiple programmers together is trying to solve that problem. Okay. So, we saw simple macro substitution where you had an identifier name and a string, very, very straightforward. Let us see whether we can do something better, or does C provide something better. In fact, you can write macros. See, remember that this string was a constant. Wherever it found this identifier, it is to simply replace that. Can I argument it? Can I make that as a variable string? So, the concept of function is borrowed, but it is not actually a function. Okay. The concept is borrowed, where along with the identifier you specify an argument list within two parentheses. Okay. All of you are familiar with this open bracket, close bracket, and a list of variable names. So, max a comma b. So, what does it do? So, you have this string, but you have the arguments written over here. You have a, b, a, b. So, this a comma b is variable actually. So, along with this max, the user is supposed to supply these two arguments. We will see that with a better example. Okay. So, all these are examples for argumented macros. So, the argument supplied to a macro can be any series of characters. For example, the definition means hash define print variable comma format printf. See, hash define print variable comma format. So, what is a string? Printf variable is equal to percentage format slash n variable. But please remember, if it is a simple macro substitution and if this print was to be out of this define, this variable was not replaced. We discussed that in the last example. But in this case, in the definition, this variable basically corresponds to this variable. This is not a constant. This format basically means this. This variable basically means again this. Okay. So, when print price into quantity comma f is called, remember this print is capital prints. So, this matches with this variable name, okay, this identifier. So, what is supplied? Price multiplied by quantity is now variable. So, variable gets a copy of price multiplied by quantity. What does format get? Format gets f. Okay. So, the resultant string for this after macro substitution would be printf, this printf, price into quantity. So, this was substituted into this and this got substituted here. I get price into quantity is equal to percentage f slash n. So, this format is basically f, then slash n, and you get price into quantity. So, you can make macros with arguments as well. You can also nest macros. We can also use one macro in the definition of another macro. So, look at this, hash define m phi, hash define n m plus 1. The moment it sees this kind of statement define m phi, all occurrences of capital M subsequent to this gets replaced by phi. So, what happens to this? So, this is defined as hash define n phi plus 1. So, now after this, wherever it finds n, wherever the preprocessor finds this token n, it gets replaced by phi plus 1, not m plus 1. It gets replaced by phi plus 1. So, the preprocessor expands each hash define macro until no macro appears in the text. Okay. I think this is very clear. So, to reiterate, when I say hash define m phi, this m can be used even in directives, even in macros. So, hash define n and I have m plus 1. So, the definition of n would be now phi plus 1. Now, subsequent to that, you see the several usage of same thing. So, for example, I have defined square and then I have the square here. I have defined cube and I use cube here even with arguments. Okay. So, we discussed the macro substitution. So, the later part of macro substitution, the arguments and all, as I said, you will appreciate when you write large programs. For small programs, probably you will not appreciate the usage of that, but still it is good to know what are the features that are available in C, so that whenever you encounter such situation, you know that I need to refer compiler directives, I need to refer hash define if I want this functionality. So, then I have one more preprocessor directives, which is called as file inclusion. An external file containing functions or macro definitions. Okay, a file will contain what? Some source code. Now, having defined or having discussed macros, it can have macro definitions, it can have functions. Okay. So, the file containing functions or macro definitions can be included as a part of the program, so that we need not rewrite those functions or macro definition. So, when I started with macro definition, I said that if there is a project and if there are 10 people doing that project and if there are set of constants which is common across all those 10 or 20 programmers, what I do is I will define all those in one single file. And what does these programmers do? Just use this file inclusion preprocessor directive to get a copy of all the constants that has been defined. So, we do that by saying hash include within quotes file and file name. You are familiar with this kind of hash include. So, with hash include stdio.h or stdlib.h. So, when you write this in double quotes, the file name is the name of the file containing the required definition of the functions or macros, and the preprocessor will search for this file name first in the current directory. Okay, when you invoke the preprocessor on a file, so whenever in the file it encounters this hash include and file name within the double quotes, it first searches for this file in the current directory. If not, then it will go to standard directories for the libraries. Whereas, if you use this less than symbol and greater than symbol, it by default it only searches in the standard directories. That is all the definition. So, now this is generally the user defined. So, normally we keep it in the local directory, in the source directory. So, let us quickly try to understand this. Let us assume that we have created the following 3 files: syntax.c, stat.c, test.c. So, basically it contains syntax definitions, statistical definitions and test functions. We can make use of the definition or functions contained in these 3 files by including them in the program as follows. So, the first line you are all familiar with. The next 3 lines are basically the one that we are discussing. So, what happens now? Whenever the preprocessor sees hash include within double quotes syntax.c, it will search for a file called syntax.c in the current working directory. So, generally this is found in that directory, otherwise it will go and search in standard lib. Okay. So, it searches for these 3 files and substitutes that. You can also have your own definitions after that, and then you write your programs. So, what happens? This particular file is now included into this file. Okay, it gets substituted into the file. Okay, so we'll see that once I get a chalk. Okay, so what I have here, I have syntax.c. So I have test.c. I have one more file. Let me not name it. So I have this file. Now let me call this as a.c. So I have stdio.h and then I have syntax.c. What happens? This entire file is copied into this. Okay, this entire file gets copied into this. And then you have test.c. This entire file gets copied into this. And the output of the preprocessor is this big file. That's all. Okay. And then if this contains some functions if this contains some functions and this contains some definitions, all those will be available for the rest of the program. This is how the large projects gets implemented. Okay. Having discussed the file inclusion, we will see some of the confusions and dilemmas that we will get into. Please imagine yourself that you are writing very large programs and you have a team developing this program. So while developing large programs, you may face one or more of the following situation. You have included a file containing some macro definition, for example syntax.c here. It is not known whether a particular macro called test has been defined in that header file or not. You have declared, you know that there is some definitions here that has been copied here, but when you actually write the program here, you may be in a dilemma whether test has been defined in the earlier definitions or not. Okay. So what would be the brute force method? You go and search for the test in this file. Okay. But if the syntax.c is developed by somebody else, so the programmer who is developing here will not be, or he should have enough say control to see whether a particular macro or a particular definition has been defined or not. Okay. So if the programmer wants to know whether a particular macro has been defined in that header file or not, so however you want to be certain that test is defined. If it is defined earlier, it's all right, but if it is not defined, you want to define it. Please remember, if you define it twice, it is an error. If I say hash define m100 and again somewhere down the line, if I again say hash define m100, it is an error. So this control, or this is the dilemma that he gets into. So we'll see how to handle that as well, because he wants to test, and if it has not been defined, he wants to define it. Second, suppose a customer has two different types of computers. So I have a customer, for example VTU is a customer. So they have an Unix machine and they have a Windows machine, and I am a vendor to that organization. VTU is the customer. I am writing programs for VTU, and VTU tells me that, look, I want your application to be compiled and run on Unix machine as well as Windows machine, because I have that. I have already made some investment on that. Okay. So how do I address that? Because the way in which you write C programs for Unix machine is slightly different from how you write for Windows machine. So you will have a certain block of statements which are OS dependent. How do you control that? You are developing a program for selling in the open market. So VTU, I know, they gave me the specification. They told me, look, I have a Unix machine and a Windows machine. I have Unix machines and I have Windows machine. Your application has to be compiled and run on both the machines. Okay. But there are, when I want to develop a product, I don't know on which machine it's going to run. Okay. So how do I see that? I write in one program and see that the actual set of lines gets compiled and run on a machine which is particular. Okay. So we'll see that as well. Suppose you are in the process of testing your program. So, all of you have done this. I think I should have put this fourth point as the first point, but I am putting it in the last because the compiler directives that we are discussing now is basically given for the first three kinds of problems, but a side effect is that it comes in handy for small programs as well. See, most of you have written programs. So, most of you would generally write what? A print statements. You write print statements to see whether your program is running appropriately or not. So, primarily you use print statements for debugging. I need not discuss it further. Now, you want the machine to execute the printf statements only when you want to debug, and once you know that the program is bug free, you do not want the machine to run those print statements. So, how do you control that? So, across all these four problems, the solution or the kind of solution that you are looking is same. You want certain statements to run based on a particular condition, and that is exactly why some of the directives are provided. So, we want to ensure that the macro test is always defined. So, this is the first problem that we are talking about. So, we have some files, header files. I want to know whether test has been defined. If the test is not defined, I want to define. So, hash include define.h. So, I do not know whether test is defined in define.h or not. I can test that by saying if not defined, if and def, if not defined test, define test1. So, this is what I want to define, and then end if. So, what happens? The preprocessor knows whether test is defined or not. If it is defined, it will not do this. It will not process this. If it is not defined, it will process this. So, the programmer is ensuring that test is defined. So, define.h is the header file that is supposed to contain the definition of test. So, this will test that condition. So, I hope you have understood this clearly. If already defined, so what is there in the if def block is no. So, similarly, in the case we want the macro test never to be defined. So, for example, if I want test, I want to just check whether the test is defined. If it is defined, I want to undefine it. So, this is how we do. If def, this is exactly the reverse of if and def. If and def will check whether it is not defined. So, this will check if it is defined. If def test, I will just say undef test. Undef means remove the definition. So, from now onwards, for the preprocessor, test is not defined. Okay. Let us look at the situation 2. That means a customer like VTU, and I am developing them for the applications. So, what do? I say if def IBM PC, expand this, else expand this. I write code for Windows here, I code for. So, somewhere in the header file, I will define whether it is Windows machine or a Unix machine. Now, if this line hash define Windows is present, it will create only this. Okay. So, this should be actually IBM PC. So, this will unfold only this. This is not executed. If I write hash define Unix, so it will be combined. So, whenever I compile on a Unix machine, I will define hash define Unix. If I want to compile on Windows machine, I will say hash define Windows. Situation 3 is similar to the previous situation. If def ABC, I have a group of lines. If it is not defined, I have a group of lines. So, this is the ABC is a customer, it wants some features, I will put that. For everybody else, I do not put that feature. So, group A lines are included for the customers ABC, and the other one for the rest of the. Okay. So, this particular example, which is more familiar to you, where we use the printf statements for debugging. So, this is what you do. If def test, you do this, otherwise you do this. Okay. So, again we will revisit this situation once again in our next session. So, at this point of time we will stop. Tomorrow we will continue with this and recap this and continue with this, and we will take a different topic called data structures. Thank you.